All right, so this lesson here is really about using logarithms to work with exponential expressions or just solving logarithmic equations as they are. But a lot of this will be connecting back to what we did in Chapter 7 and using what we've learned in the last few days about logarithms to basically solve exponential equations. But first, before we get to anything applied, here I have two exponential equations and I want to solve them both algebraically. And there's two basic approaches that I kind of recommend. I'll show one for each, and they're all the same thing. Ideally, you understand both. But one approach for, like I'll do for the first one, is to, when we have an exponential equation, which means your variables in the exponent, is to log both sides. And just basically find the logarithm of whatever base you want of both sides. And usually we use log base 10 because that's what's on any scientific calculator. So I'm going to write this as log of 5 to the power of x over 2 equals a log of 200. I can pick any logarithm I want, though. So I'm going with log base 10. The point of that is now this x over 2, I can now use the power law to write it as a coefficient. So I have x over 2 x over 2 times the log base 10 of 5 equals the log of 200. And now I can multiply both sides by 2, and so get x times the log of 5 equals 2 times the log of 200. And then I can divide both sides by the log of 5. And so I can see how x will equal 2 times the log of 200 divided by the log of 5. And it doesn't matter what logarithmic base I pick, as long as it's the same. And again, every scientific calculator has a nice big log button, so that's one common thing. And if you decimalize this, which I don't really care about too much, you get about 6.58. So x equals about 6.58. Another approach, which would get you the same answer, which I'll do for the second equation, is to at some point write your equation from exponential form into logarithmic form. Now I can't do that yet because I have that coefficient of 5,000 in front of my exponential expression. Again, to put something in from exponential form to logarithmic form, you want to have, you don't want a coefficient in the front. That's it. It's easy to take care of. Divide both sides by 5,000. And so I get 1.2, or 6/5 on one side, and 1.02 to the power of 12x on the other. Now I could log both sides, just like before, or what I can do, I can take something that is in exponential form and write it in logarithmic form. And we've been doing this lots in the last few lessons. So in logarithmic form, it always starts with log base. What's the base? Well, it's the base of the exponential function, which is 1.02. So log base 1.02 of 1.2 equals 12x. And now to solve for x, all I got to do is divide both sides by 12. And so x is going to equal kind of a weird, messy logarithm, but that's OK. X equals the log base 1.02 of 1.2, all divided by 12. Now that's it. Nothing wrong with this logarithm here, but it looks kind of weird. And however, I don't have to leave it like this. So everything you see right here, we saw last day, it can be rewritten in this case as the log of any base I want, maybe log base 10 of 1.2 divided by log of 1.02. So what you see here is equivalent to what you have above once I divide by 12. And so I could say divided by 12 at this point, or I could write it, dividing by 12, same as multiplying by 1 over 12. So if I want, I could just put the 12 right here. It's all the same thing. And even if your calculator does have a button like this, in which you can type in any logarithm you want, just make sure you understand how to go from here to here. That is an expectation to understand that everything you see here is equivalent to everything you see here. And that was explained in the last lesson. That's it. I don't care how you use your calculator. In this case, you should get about 10.5. So x is about 10.5. It's all the same thing. Really, ideally, you should understand both. If you feel really good that you understand one but not the other, well, then you don't understand something. And that's eventually something we want to deal with. All right, let's look at solving a logarithmic equation. And so these are two equations that have a variable instead of logarithm. And so how do we solve something like this? Well, first of all, is we want to put it into a form in which we can eventually change it into exponential form. And right now, they're both too messy. So right now, I can't put this in exponential form because there's too much going on. I need to have just a single logarithm. The good thing is we've learned about these logarithm laws. Well, actually, even before that, I take that back. If I look at the right side of this, there's no variables there. That's just 1 plus the log of 2, which means 1 plus log base 10 of 2. I can just type that into my calculator, actually. And if I do that, I get about 1.3, or 1.30. It's actually very close to 1.3. So I didn't actually need any logarithm laws here because, again, the right side had no variables. And now, what I have here is in logarithmic form. I want to put an exponential form. Remember, this is log base 10 of x. So in exponential form, this is 10 to the power of about 1.3 equals x, or approximately x, because I did round that 1.3. OK? And there we go. X equals about 10 to the power of 1.3, or about 20. It's very, very close to 20. Now, I will say it actually is exactly 20. And I can see it's exactly 20 if I work this out a different way. Okay? And I say right now it seems like it's approximately 20 because that 1.30 at the top has been rounded. But if I do this another way, I can actually show you that it's exactly 20 without even using a calculator. And there's always going to be countless ways of doing this, but that's it. I do want to show you this. So another way, let me start by writing the question out again. Log base 10 of x equals 1 plus log of 2. OK. One thing I could do right now is I could put this into logarithmic form right now. It looks kind of messy, but all of this, again, I can think of as the output of my logarithm, so that'll become the input of my exponential equation. And again, this is base 10. And so I can write this in exponential form right now as 10 to the power of 1 plus log of 2 equals x. OK, but like I said, I can get to 20 exactly without having to round anything. So how? So this looks kind of messy, but the good thing is, again, everything you see highlighted in green is a constant, so it's not a variable at all. That's it. I have that 10 to the power of 1 plus log base 2. I can use my exponent laws backwards and write this as 10 to the power of 1 times 10 to the power of log of 2. And again, if you look at this in reverse, it's probably more obvious. I'm multiplying two powers of the same base. When you multiply powers of the same base, you can add your exponents. And if that works that way, I must be able to do it in reverse. So what I have here is 10 to the power of 1, or just 10, times 10 to the log of 2. But don't forget, that log of 2 means log base 10 of 2. And 10 to the power of log base 10, those are inverses of each other, so they must cancel out. So I know this must equal just 10 to the power of 1, or 10 times 2. So that, without actually using a calculator, I know this equals 20. That's it. Algebraically, it's more complex than before, but again, I now actually know this is exactly 20. However, nothing wrong when I did it up there. This definitely was harder, I think. But let's look at this one. OK. Definitely too much going on for me to put this in exponential form too soon, but I can take both of these right now, and I can realize I'm adding two logarithms with the same base. And so we saw from one of our logarithm laws that when you're adding logarithms with the same base, if you want, you can write them as a single logarithm where you're multiplying these inputs. And if I write it like this, I now have something that is still a bit messy, but it's not as messy as before. There's less stuff going on. I have a single logarithm equaling a value. I can put this in exponential form. Is 15 to the power of 1 equals 3 minus x times 1 minus x. Well, what I have now is a quadratic equation. And so let's expand and simplify the 3 minus x and the 1 minus x. And if you expand and simplify that, you get x squared minus 4x plus 3. I just FOILed it out, collected like terms, and wrote it in a more standard order. That's it. Like I said, this is the makings of a quadratic equation. Quite often, we can factor them, and even if we can't factor them, we probably want to make it equal 0. So I'm going to subtract 15 from both sides and get 0 equals x squared minus 4x minus 12. If we can't factor this, we'll use the quadratic formula, which again needs it to equal 0. That's it. This can factor. and I get x minus 6 and x plus 2. That said, the solutions to the quadratic equation are 6 and negative 2. Again, these are solutions to the quadratic equation. But don't forget, I didn't give you a quadratic equation. We start off with a logarithmic equation. So here's where we have to be careful. Quadratic equations have no restrictions. You can, if I go back to this step right here, you can put any number you want into x. Quadratic equations have no restrictions. Logarithms, though, do. I can't put any number I want into a logarithm. Logarithms have to have positive numbers being inputted into them, right? The log base 15 of 1 makes sense. That means 15 to the power of what equals 1? That must be a 0. And any positive number makes sense. But log base 15 of 0 does not make sense, because that means 15 to the power of what equals 0? That's not possible. Or negative numbers don't make sense. Log base 15 of negative 2 means 15 to the power of what equals negative 2. And again, I can't take 15, raise it to a power, and get negative 2. And so we got to be careful, because yes, I solved a quadratic equation, but there's a good chance I've missed some restrictions. There's a good chance I have to reject at least one of my answers. And all I have to do is check my two solutions here by bringing them back into my original equation, here and here. And all I have to do is make sure when I replace x with 6 or I replace x with negative 2, I just have to make sure the input of the logarithm is greater than 0. So I'll kind of make a note here, and then I'll check. So I need to check. Oops, I got to learn how to spell check. Okay, so I'll say again, the input of a logarithm must be greater than 0. That's all I have to check. If I, assuming I haven't made any algebraic mistakes, if I replace x with a 6 and I get an input that's negative, I have to reject it right away. And notice I see that right away. If I replace either of these x's with a 6, all that matters though, if it happens as a single case. But I can see here, with both my x's actually, if I replace them with 6, I get 3 minus 6, which is negative 3, which means log base 15 of negative 3. That makes no sense. So how on earth can 6 be a solution to an equation if it doesn't even make sense putting into the logarithm? At that point, I need to reject it. That's not a solution. Check with negative 2. Negative 2 works for both. Put a negative 2 right there. 3 minus negative 2 is 5. That's good. Check right here. 1 minus negative 2 is 3. We're good. And so that's all I have to do. Just make sure there's not a negative value in there. And so therefore, I'll say x equals negative 2 only. And this will happen a lot when dealing with logarithmic equations. Because quite often when you're solving a logarithmic equation, at one point you start dealing with a quadratic or a linear equation. And quadratic and linear equations don't have any restrictions, but logarithms do. You can't put negative numbers into a logarithm. It just doesn't make sense. But notice my solution was negative, because when x is negative 2, both my logarithms end up having positive values inside them. So please don't make the mistake of assuming anytime you have a negative value right here, it must be rejected. In this case, it was the other way around. My positive one had to be rejected. In the end, there's no simple rule like if it's negative, it's wrong. It's still fairly simple. Just go back and check. Just check and see if the input of the logarithm is negative. Okay, so with that said, let's look at some applied questions. All right, how long will it take to the nearest month for $12,500 to grow to $20,000 if it's invested at 10% compounded monthly? So first, let's set up an equation here. I want $20,000 to come from $12,500. It's growing at 10% monthly. So that means it's the same as 1 plus 10% divided by 12. So every month there's that much money being added. But if I want my variable up here to be in years, which I would like it to be, I want 12 times the number of years. I'll put a t. Now again, I did this quite quickly because I talked about this in chapter 7. But again, what you see all highlighted in blue comes back to that 10% compounded monthly. And so t I know was in years. If I didn't have a 12 there, if I just had a t, it wouldn't be wrong as long as I know what that t meant. If I have that now that means my t is in months, because every month that's how much money is being added. And as long as I know that's in months, I can work with it. But that said, chances are we probably want to think in years. So I'll go back to this. All right, so now let's solve this. Let's divide both sides by 12,500 first. So we get 1.6 on one side, and I'll just stick with this 1 plus 0.1 over 12 to the power of 12t. I could decimalize it, but honestly, I don't know if the decimal's any nicer. And this is exactly what I have right here. So next, I could put this in exponential form. Sorry, I could put this in logarithmic form, or I could log both sides. I'll log both sides. So find the log of 1.6 equals the log of all of this. The whole point of logging both sides is that 12t I can now write as a coefficient. Great, trying to solve for t. At this point, if I want to solve for t, I want to divide both sides by 12 and divide both sides by that log 1 plus 0.1 over 12. So yeah, it's going to be a little bit messy, but I can see t will equal log of 1.6 divided by 12 times the log of 1 plus 0.1 over 12. And yeah, it's a bit messy, but your calculator doesn't care. And if you type this in properly, and again, be careful, there's a lot of stuff going on, but t should be about 4.7, which is going to be in years because I set my equation up to be in years. Keep in mind, if I didn't have that 12 at the top, if I zoom out, if I didn't have that 12 right there, then all along every step wouldn't have a 12, which means there wouldn't be a 12 right here, which means my answer would again be 12 times more, which would make sense because I said at the beginning, if you didn't have that 12, your answer is in months. But in this case, I think it's better to think in years since we're going so far past a year. Okay, but I never specified the time unit. And again, you always have choices. The key is, do you understand what you've done? All right, let's look at this question. How long will it take 20 milligrams of iodine 131 to decay to 16.85 milligrams, knowing the half-life of iodine is just over 8 days, 8.1 days? Again, let's set up an equation. So I want 16.85 to come from 20. It's a half-life question. So I'm telling you how long it takes for iodine to lose half its mass. And it loses half its mass not every day, every 8.1 days, which means I'll have x here. Oh, I'll put t for time again, actually. And this time my time is in days. But if I just leave it like this, if I just leave it as t, that would be correct if the half-life of iodine 131 was every day. If every single day it lost half its mass, but it's not every day, it's every 8.1 days. And so again, everything you see highlighted in blue is connected to one another. And now again, I want to solve for t. Regardless of how I'm going to do this, I want to start by dividing both sides by 20. And so I get a 0.8425 on one side, and 1/2 all to the power of t over 8.1. This time, I have an equation exponential form. I'll try writing it in logarithmic form, just for something different. So in logarithmic form, it always starts with log base. Well, what's the base of my exponential equation? The base is 1/2, or 0.5, of 0.8425 equals t over 8.1. And I'm pretty much done at this point. Or I'm ready to go to my calculator at this point. And so multiply both sides by 8.1, and it's totally correct to say that t equals 8 times the log base 1/2 of 0.8425. And that is totally correct. However, again, I want you to make sure you understand that everything you see right here is also the same as the log of any base, log base 10 I'll go with, of 0.8425 divided by the log of that same base of 1/2, or 0.5, so times 8. And again, depending on your calculator, you may have to change it into this form. But even if you don't have to do that, I just need you to understand that. Okay? Essentially, I'm changing the base of a logarithm from base 1/2 to base 10. You should get about 2 hours. Sorry, not 2 hours, 2 days. There we go. The half-life was 8.1 days, not 8.1 hours. All right, so then what's left is the final problem, in which I have some actual data that shows the total number of Facebook employees worldwide from 2004 to 2008. and it has the characteristics of exponential growth. So I want to model it and then kind of go with it. Okay, but this does have, this looks exponential-ish at least, although it is actual data showing how many employees they had around the world. The first thing I want to do is create a model. And we got to be clear what I want the model of. I want to model the total number of Facebook employees, and I want to call that N, to time, which is years from 2010. Okay, I want years from 2010. And then eventually I want to use that model to predict when they'll have 100,000 employees. And that again assumes they keep growing at in an exponential rate, or exponential way, I should say. That's it. What's my model? Well, if I want to start in 2010, if I want 2010 to be my starting point, let's look at the year 2010. In the year 2010, there was 2,127 employees around the world for Facebook. And so that's going to be my starting amount. And notice for all our exponential equations, our starting amount is our coefficient of the exponential form. So 2,127. That's it. Here's the main thing. What's the base? And what's the power? Well, I always have a choice. One thing I could do that I don't recommend is to find out how much it's going up by in terms of multiplying every time. And I don't recommend that because, first of all, you may just look at the first jump, 2,127 to 3,200. For example, if I go 3,200 divided by 2,127, I get like 1.5, okay, which is 50% growth roughly in a year. That said, it's a terrible assumption to say that that must be the case for everything else. If I made up the data and I told you this is a perfect exponential model, or this data is growing perfectly exponentially, then that's all you need. But I said right from the start, this is actual data. So if we look at the next year, 4,619 divided by 3,200, then it's growing by about 1.44 from here to here. And if I really want to keep going with this, I need to keep checking out pretty much all the steps, or at least a lot, to try to come up with something that seems about a reasonable average. However, what's actually better and is less work. I say better because it's or roughly just as good as finding all the steps and then finding an average, is just to do it in one big step. Let's see from here to here. What do I have to multiply to go from 2,127 to 35,587? Well, I don't know, but I go to my calculator and go 35,587 divided by 2,127. And if I do that, I get about 16.731. And so from 2010 up to 2018, Facebook, the total number of Facebook employees grew more than 16 times, almost 17 times more employees. So how can I use that? Because that kind of takes into account a whole bunch of years for me. So I can make that the base of my exponential expression, either the fraction or I'll go with the decimal, about 16.731. There's no rule saying you have to go up in 1 year. In fact, we've seen lots and lots of examples where we're not going up in 1 year or 1 day. The very last question was like that. I said the half-life was every 8 days, and that didn't throw us off. I basically told you every 8 days it loses half its amount. So I'm here, if we look at this, and like I keep saying, we have lots of choices. I want to be as accurate as I can without rounding needlessly, without making it needlessly messy. And so at this point, what's my power? Well, if I put just a t right here, that would be if every year Facebook grew 16.7 times more. But it wasn't every year. That was from 2010 to 2018. That's 8 years. So divide by 8. And this model here will be just as accurate as actually finding every single one of these and kind of finding an average of them with so much less work. So yeah, it's better. It took significantly less work to come up with an equally accurate model. And if it seems strange going in a big jump like that, well, did it seem strange right here? Because that what you see highlighted in blue is essentially the same idea. I told you it took 8 days to be cut in half. Well, here I'm telling you it takes 8 years to multiply to grow about 16.7 times. Now that I have this, that's the main part of the question done. At this point, if you want to solve for how long it takes to reach 100,000, you could replace n with 100,000. And then it's just like so many of the previous questions. Then you could solve by at some point putting it in logarithmic form, or you can log both sides. If you do this properly, I'm not going to go through all the steps. You should get about t equaling about 10.9, I believe, if I did my calculations correctly. But again, 10.9 years from what? from 2010, because that's how we chose to set up, well, that's how we were told, actually, to set up our model. And so that would mean, in this case, about the year 2021, assuming it kept growing in this form. Okay, and at some point, it has to stop growing exponentially. If it didn't, then within a matter of a decade, the entire world would be working for Facebook, and that's probably not realistic. So everything that grows exponentially at some point stops. But again, if it continues to grow exponentially around the year 2021, although really, it was coming up with a model like this that was key to this question. And again, there are so many other ways of coming up with an equally good model, but they're probably not as quick. And that's where I'm going to stop.